Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Today it's my great pleasure to welcome MURAD ÖZAYDIN from the University of Oklahoma, and he will speak about non-commutative algebraic geometry of Leavitt path algebras, or if you want, Hilbert Nullstellensatz version for Leavitt path algebras, and it's based on joint work with Aiden, who is also in the audience, so we can fire at will at both of them. Guys, it's all yours. Take it away.
Thank you, Piotr, and thank you for letting me have this opportunity. So, as Piotr already mentioned, it's joint work with Ayten. Let me just start without further ado. If we look at a quotient of the algebra of polynomial functions on an affine variety, when over an algebraically closed field, then that quotient is isomorphic to another affine functions, regular functions on an affine variety, if and only if the radical of the quotient is trivial. This is equivalent to Hilbert's Nullstellensatz. And one of the results I want to mention is the analog of this for a Leavitt path algebra. That is, the quotient of a Leavitt path algebra is isomorphic to some other Leavitt path algebra, if and only if the radical of the quotient is trivial. Now I'm going to define pretty much everything that's reasonable, but I want to mention that a basic goal of non-commutative, in this case algebraic geometry, is to extend the correspondence between this duality, affine varieties, finitely generated reduced commutative algebras, or in the topological or analytic setting, the duality between compact Hausdorff topological spaces and commutative unital C-star algebras, to a non-commutative setting. So from this perspective, the result mentioned suggests that Leavitt path algebras seem to behave like non-commutative function algebras on directed graphs. Now, there is a bridge between the algebraic story and the analytic story, which is given by the Stone-Weierstrass theorem, which basically says that polynomial functions are dense, while polynomial functions and their conjugates are dense. And the corresponding result between Leavitt path algebras and their completions, which are graph C-star algebras, also exists. That is, the completion of a Leavitt path algebra with complex coefficients is a graph C-star algebra. Now, to streamline a lot of ideas that will come up, I like the concept of Galois connection. And in fact, every math talk is supposed to contain a proof and a joke. Instead, I will give you two trivial proofs immediately, getting them out of the way, and no joke. At least no intentional ones. It's already April 1st. That's enough of a joke. So, a Galois connection between two partially ordered sets is a pair of order reversing maps satisfying the condition that when we look at the compositions, it's increasing. So every element P of the poset capital P is less than or equal to rho lambda of P. And the same for the other poset, Q is less than or equal to rho lambda of Q. Now, immediately we have an easy lemma. If we have a Galois connection, then the triple compositions are the same as just one of the appropriate one of the order preserving maps. So to see the proof, if we start with the second condition of the Galois connection and apply it to something that's in the image of lambda, so putting Q is equal to lambda of P, we get that lambda P is less than or equal to lambda rho lambda of P. On the other hand, if we take the first condition of the Galois connection and apply lambda to it, then we get lambda p is greater than or equal to lambda rho lambda p, because the maps are order reversing. Then, by the anti-symmetry of the poset, we get that lambda rho lambda of p is equal to lambda of p for every p. Therefore, lambda rho lambda is equal to lambda. And the argument, of course, is completely symmetric. So the same thing is true for rho lambda rho, which is equal to rho. Now, it follows from this theorem that we get a one-to-one correspondence. Now, if we have two functions between two sets, usually we want to find subsets so that we have a one-to-one correspondence when we restrict the functions to those subsets. And in this case, when we have a Galois connection, this is achieved in the best possible way. Obviously, the subsets we have to take have to be at least the image of each function. And in fact, when we restrict lambda and rho to the image, respectively, of rho and lambda, then these restrictions give a one-to-one correspondence, which is called, for obvious reasons, a Galois correspondence. So here is the easy proof. When we are looking at the composition lambda rho, by the way, I compose from left to right, not from right to left. So when I say lambda rho, that means first apply lambda, then apply rho. If we start with an arbitrary element in the image of rho, so that looks like rho q, and apply rho lambda to it, we get rho lambda rho of q. But by the lemma, that is equal to rho q. So that says the composition is identity. And the composition in the other order is also identity for the same reason. So when we restrict to the images of lambda and rho, we get one-to-one correspondence between the images. Now, the compositions, the twofold compositions, rho lambda and lambda rho, are also called closure operators on P and Q. What that means is they are idempotent and increasing. So if you apply it twice, that's the same as applying it once, which of course follows immediately from the lemma. And anything, when you apply it to anything, you get something greater than or equal to it. And that, of course, is part of the definition of the Galois connection. Now, let's look at the case of the Galois connection in the classical setup of Hilbert's Nullstellensatz. We take the partially ordered set of all subsets of the affine space Fn under inclusion, that's the partial order. And for the other poset, we can take the ideals of the polynomial algebra in n variables. Again, under inclusion. And we have a Galois connection, which says that the ideal corresponding to a subset is the ideal that vanishes on that subset. It's clearly an ideal, easily checked. And in the other direction, we have the zero sets of ideals. So given any ideal, we look at the points that every element of the ideal vanishes on. Now, if we take just a singleton as our set, say the ordered n-tuple A1 through AN, clearly the functions xi minus ai vanish on that set. So the ideal, contains the ideal generated by xi minus ai, but that's a maximal ideal. And we know that not every function vanishes on the point A1 through AN, because the constant function 1, for instance, does not vanish. So the ideal that corresponds to a singleton is clearly the maximal ideal generated by xi minus ai. Now, in the converse direction, we may start with a maximal ideal and ask what is the set, its zero set. Now, for this to have a nice answer, we need a further hypothesis, and that is the field is algebraically closed. And that says the converse is exactly true. That is, if you start with a maximal ideal and look at its zero set, it's a singleton. And that's usually termed the weak Nullstellensatz. By definition, a variety is the zero set of some ideal. That is something in the image of the order reversing map between the posets. It is also a Zariski closed set because we have the Zariski topology to have a closure operator to define a topology. You need another condition, the Krotowski condition, but I won't get into that now. But in this case, it's satisfied. Now, an ideal is in the image of the order reversing map if and only if it's a radical ideal. So a radical ideal, that means it's equal to its radical, which is the set of all elements, a power of which is in the ideal. And this is true, again, with the hypothesis that the field is algebraically closed, and it's usually termed strong Nullstellensatz. And we define the ring of regular functions or the algebra of regular functions on the variety Z as polynomials divided by the ideal that sends Z to 0. And obviously, when we think of them as functions, they are identified if they vanish or their difference vanishes on the ideal of the variety. Now, any commutative finitely generated algebra is a quotient of the polynomial algebra. If it has trivial radical, then it is isomorphic to an algebra of regular functions on some variety. And when the field is algebraically closed, the quotient is an algebra of regular functions on the variety, if and only if the kernel is a radical ideal. In other words, the only obstruction to a quotient of an algebra of regular functions on a variety, a fine variety, to be isomorphic to an algebra of regular functions on some other variety, which in this case turns out to be a subvariety, is the radical of the quotient. That is, the radical of the quotient needs to be trivial. Now, the topological story is, of course, the Gelfand-Naimark duality, which says that continuous complex valued functions on a compact Hausdorff space forms a commutative C-star algebra, a unital commutative C-star algebra, and we can recover the space from the C-star algebra as the space of maximal ideals. In fact, this gives an equivalence, this is functorial, between the category of compact Hausdorff topological spaces and unital commutative C-star algebras, except it's a contravariant functor. So we get the opposite category of 1, whichever one you want to choose. Now, again, a goal of non-commutative topology geometry. It's called non-commutative geometry, but this is really more like non-commutative topology, is to extend this duality to certain non-commutative C-star algebras. And as I mentioned before, the bridge between the affine variety radical ideal duality and the Gelfand-Naimark duality is given by the Stone-Weierstrass theorem, which says that polynomial functions and their conjugates are dense in the algebra of continuous functions. And of course, we are taking the infinity norm, the sup norm, of compact subsets of affine varieties. And we have the analogous theorem for Leavitt path algebras and graph C-star algebras, which says that the completion of a Leavitt path algebra with complex coefficients is the graph C-star algebra of the same digraph, and that you can think of as a non-commutative Stone-Weierstrass theorem for Leavitt path algebras and graph C-star algebras. Now, I actually want to define, even though I suspect most of you know what I'm talking about, but I want to define Leavitt path algebras to establish notation and to give a few examples, because thankfully I have 90 minutes. So a directed graph is a four-tuple: vertices, arrows, and the source and target functions from the arrows to the vertices. If a vertex is not the source of any arrow, then it's called a sink. And if a vertex is not the target of any arrow, then it's called a source. And an arrow which has the same source as its target is called a loop. We call the directed graph digraph for short finite if both the vertex set and the arrow sets are finite. And today I will take gamma to be finite from now on, which will simplify the discussion. But in fact, essentially everything I say will also be true for arbitrary digraphs. Now, a path of length n is, of course, a sequence of arrows such that the target of each arrow is the source of the next arrow. And we think of vertices also as paths of length 0. And the source of a vertex and the target of the vertex is, of course, itself. And the length of a path is the number of arrows involved in the path. A cycle is a path with the same source as its target, but so that we have no repetition of the vertices other than, of course, the source and the target of the path. An exit of a cycle starts at some vertex, has source equal to some vertex on the cycle, but it is not one of the arrows of the cycle. Now, the path algebra of a digraph gamma with coefficients in the field F, which we denote F gamma, is formal linear combinations of paths. And addition is, of course, pointwise of linear combinations. Multiplication of two paths is defined to be 0 if the target of the first is not equal to the source of the second. Otherwise, it's the concatenation of the two paths, PQ. So a basis for F gamma by definition is all paths in gamma. Now, the doubled digraph is obtained by adding a dual arrow for each arrow in the digraph. So in the double digraph, we have the same set of vertices. The arrows are doubled. We have the original arrows and their duals. And the source and the target for a dual arrow is the reverse of that of the original arrow. So we have these arrows, the dual arrow has switched its direction.
Sorry, I just got a stupid, let me jump in. Question is the first time I see it called double graph. I always would call it extended graph.
I think the standard graph theory terminology is doubled graph. Now, of course, you will see that in Leavitt path algebras, a lot of terminology and also graph C-star algebras was created without paying attention to the existent terminology in other areas that were, some of them were well established. In particular, I want to say you guys, but I should hold myself. Say graph instead of a directed graph, which to me has edges which have no direction. And since edges have no direction, I call it arrows, not edges, etc., etc. I don't know whether I answered.
I morally agree with you. I don't like the idea of calling it a graph. I would call it a quiver. I think this is a much better name. And I much more prefer arrows to edges. But you cannot go against 100 published authors. And this is why I kind of succumbed to this terminology. I mean, I don't like it, but it's not offensive. But yeah, I mean, I have nothing against double graph. It's just I've never seen it used before. So you say that people who do combinatorics of graphs call it double graph.
People who do graph theory.
Graph theory, yeah. Mm-hmm.
Yes.
Okay. Okay.
Yeah.
Good to know. Good to know.
Yeah.
Yeah, just a technical remark. The sound quality is somehow disturbed.
Sorry?
For Piotr, that sound quality is somehow disturbed.
Even now?
When you are speaking for a longer period of time, sometimes there is some noise.
Yeah, that's the eternal problem, which I cannot help. Yeah, thank you for. Yeah, that's this time. Because there are just two of us today, I decided not to use these microphones that you clip on, because I thought that maybe this was the source of static, but it turns out that even now, when I'm 20 centimeters away from the microphone, you still complain about static.
Yeah, so this is the same issue, the same kind of noise as usual when there is a problem.
Yeah. Mm. And I took care this time of switching on and off the magic box, so it's okay. Okay, thank you for telling me. Okay, thanks.
Yes, so coming back to the definition of a Leavitt path algebra, we take the path algebra of the doubled digraph, and then we divide it by the ideal generated by the relations, Kunz-Krieger relations. And the first family of Kunz-Krieger relations says that a dual arrow times itself is equal to the target vertex of that arrow, but a dual arrow times any other arrow is defined is zero. And the second Kunz-Krieger relation says that every non-sync is equal to the sum of the products E star, where the arrows E run over all arrows that have source equal to the vertex V.
Even if the sum is infinite?
I already assumed that the digraphs were finite. Today, all digraphs are finite. You are correct, of course. If I was giving the definition for an arbitrary digraph, then I would look at vertices that are not sinks, but also not infinite emitters. So the relation is algebraic, so we don't have infinite sums, we only can have finite sums. Now, we have some more structure on the Leavitt path algebra, and an important one is the star algebra structure. And that is defined on the generators as the vertices are self-adjoint, so their stars are equal to themselves. The star operator is involutive, so the double star of an arrow is itself. And the star of a path is the product of the arrows in the path in reverse order, the duals of the arrows of the paths in reverse order. There is also a grading on the algebra, an integer grading, which is not going to be as important for us, but it will come up. And the vertices have grade 0. And arrows have grade 1, and dual arrows have grade -1. And you can see that that will induce a grading on the Leavitt path algebra because the relations we impose are all homogeneous, the Kunz-Krieger relations. Now, it also follows from Kunz-Krieger 1 that elements of the form PQ star, so these are paths in the doubled digraph, where P and Q are paths in gamma with the same target, span Leavitt path algebra.
May I make a quick comment? This is a very nice and subtle thing, but they span, but they do not form a basis. But they almost, I mean, you have to make some exceptions, and I find the basis theorem for Leavitt path algebras quite exciting because it's non-trivial. And of course, you cannot do much without this theorem. Also, what is extremely useful when you study Leavitt path algebras or graph system algebras, so-called graph inverse semigroup. And this PQ star would be exactly a typical element of a graph inverse semigroup. Just a remark. Yeah. Tomek, you have a question. Go ahead, Tomek.
Yes, I have a question. Forgive me, I cannot show my face because I have a trouble with the connection. My question is about coefficients. You are speaking about algebras over arbitrary fields.
Correct.
If you, yeah, so on generators, you define the star as it was an involution which is linear over coefficients, but over complex numbers, usually people are allowing to twist this coefficient by complex conjugation.
Exactly.
That's exactly correct, and it's in fact relevant. I'm sweeping it under the rug because I didn't say that it was linear or anything. I didn't really tell you how to extend it. But in case we actually have an automorphism of the field which has order 2, then we could also take the star to be like conjugation on the coefficients. So when we take, so it's not linear, it's skew linear. But for most fields, we do not have this particular involutive automorphism. So if we don't have it, then we have to take it to be linear. Yeah, but that's actually relevant when we consider Leavitt path algebras with complex coefficients, for instance. Yeah, thank you.
Thank you.
And the last remark is when we have finitely many vertices, as we will today, then the sum of the vertices acts as a multiplicative unit in the Leavitt path algebra. That is the multiplicative unit of the Leavitt path algebra. So let me give a few easy examples. We could take the digraph to be a path with n vertices and therefore n-1 arrows. And then the Leavitt path algebra turns out to be the matrix algebra, n by n matrix algebra with entries from the field. This is a special case of digraphs, acyclic digraphs that have no cycles. And whenever we have a digraph with no cycles, its Leavitt path algebra turns out to be a direct sum of matrix algebras. And we can say exactly how many matrix algebras and what are the sizes of matrix algebras, etc. But that won't again be relevant today. So let me go on to another very easy but crucial example where we have only one vertex and one arrow. So then the Leavitt path algebra, it's easily seen to be isomorphic to the Laurent polynomial algebra, where the arrow or its dual would be the generator and the other, its dual, would be the inverse of the generator. I should say, sorry, that this is also a special case of the family of examples where the digraph has cycles, so it's not acyclic, but the cycles have no exits. And in that case, the Leavitt path algebra is isomorphic to a direct sum of matrix algebras, some of them with entries from the field, so those will correspond to the sinks, and some of them will correspond to the cycles with no exits, those are the only cycles, and those will be matrix algebras with coefficients in the Laurent polynomial algebra. And these two results were proven very early, and they are not difficult to do in Leavitt path algebras by Abrams, Arandapino, and Siles Molina. Now, the next type of example is when we have cycles that have exit. And here is an example, the Toeplitz digraph, so-called because if you take the Leavitt path algebra with complex coefficients and then complete it to a C-star algebra, then you get the Toeplitz algebra. And from another point of view, I will denote it as D2Q, because this is the digraph that corresponds to a two-dimensional quantum disk. And that's the easiest.
Yes.
Sorry?
So-called Klimek-Leśniewski quantum disk.
Yes, there are now what it corresponds to, and then there is the digraph. So there is some discussion about what to call it, but anyway. Now, this is also a special case of Leavitt path algebras in general. That is, Leavitt path algebras where the cycles do not intersect. So such Leavitt path algebras, or rather such digraphs, have Leavitt path algebras that have polynomial growth. That's a theorem of Al-Ahmadi, Al-Sulami, Jain, and Zelmanov. And the converse is also true. A Leavitt path algebra has polynomial growth if and only if the cycles of the digraph do not intersect. They are called exclusive cycles. And this is the first example of that. So we still have polynomial growth here. In fact, it has linear growth, and you can easily figure out what the growth is. Now, it turns out that this algebra is also a classical or semi-classical algebra called the Jacobson algebra, where we start with the polynomial algebra into non-commuting generators, and then divide by the ideal generated by 1 minus their product, but product one way. And this is an algebra that Jacobson used for some examples or counterexamples, I think around 1959. So it's called the Jacobson algebra. And there is an isomorphism between the Leavitt path algebra given by the Toeplitz digraph and the Jacobson algebra, but I will leave that as an exercise. So the next example is where the name Leavitt path algebra comes from. And this is, in calculus at least, the digraph is called the rose with n petals. I think it should be
Hawaiian earring. It's also called the Hawaiian earring.
No, I don't think so, because the Hawaiian earring, the point of the Hawaiian earring, at least in topology, is that there is a metric, and these cycles get smaller and smaller.
But it's irrelevant because no. But when they get smaller and smaller, it's completely irrelevant because the point is that you have one base vertex and you have distinct loops coming out of it. That's it. When they get smaller and smaller, it's completely irrelevant.
Well, I think maybe we'll call it a Polish earring because a Hawaiian earring has infinitely many loops.
Really? I mean, that will be hard to forge out of metal.
Yes, that's why it's Hawaiian. Anyway, so I'm sorry, there are these unintentional jokes that are cropping up. But as you see,
it's Prima Aprilis, it's 1st of April, so we can fool around.
We can indulge. So this is, of course, an example where cycles do intersect, and it's the easiest such example. And the Leavitt path algebra of this particular digraph is the Leavitt algebra 1n, and the generators and relations are exactly the Kunz-Krieger relations that come up, and that's what Leavitt defined in the late 50s and early 60s, and proved some very nice results about the extent of the failure of the invariant basis number property. in algebras. Of course, Leavitt was not doing anything with digraphs. This is the only example he had, and you can write down the example without mentioning any digraphs. Okay, so let us go to the next topic. And in general, there is this philosophy in Leavitt path algebras of finding a dictionary between geometric properties of the digraph and algebraic properties of the Leavitt path algebra. And on the geometric side, we say that a subset of vertices is hereditary if the source of an arrow is in the subset, then the target of the arrow is also in the subset. And we say that a subset of vertices is saturated if all the arrows with vertex V have targets in the subset, then the vertex is also in the subset. But we only say this, we put this condition on only for vertices that are not sinks, because we need to talk about the arrows that are emanating from that vertex. Now, and then again, an easy and fundamental result is if you have an ideal of a Leavitt path algebra, then the intersection of that ideal with the vertices is hereditary and saturated. Of course, here we are thinking of vertices both as geometric objects and also as idempotent elements of the Leavitt path algebra. So we can talk about the intersection of the ideal with the vertex set, or the vertices that are contained in the ideal. So the vertices that are contained in any ideal form a hereditary and saturated subset. Now, we can construct another directed graph when we have an ideal of the Leavitt path algebra, and we do that simply by erasing the vertices that are in the ideal. So gamma slash j is the digraph we get by deleting the vertices in the ideal j. And of course, when we delete those vertices, we also have to delete any arrows touching these vertices with source or target equaling to these vertices. And what we get out of this construction is we have a star algebra epimorphism from the Leavitt path algebra of gamma slash j to the Leavitt path algebra, the original Leavitt path algebra, divided by the ideal j. And this is the obvious homomorphism, which sends vertices to themselves or their cosets defined by them, and similarly for the arrows. And of course, because it's a star algebra morphism, the dual arrows have to go to the cosets defined by the dual arrows. And this epimorphism is an isomorphism if and only if the ideal J is a graded ideal. Now,
I'm sorry, I just have slight discomfort seeing the notation that you divide the graph by an ideal.
Yes.
Well, I understand what you mean, but it is really not appropriate in my opinion.
Well, if you can come up with another notation. By the way, we have, you will see that.
It's obvious, LF gamma divided by J. This is how you should do it, not gamma by J.
No. L of gamma divided by J is different from the Leavitt path algebra.
Okay, because you mean a subgraph that you obtain by deleting these guys. Okay, yeah, okay.
Yeah. We have debated about these notations, and there's going to be another one, gamma double slash J, that's going to come up later, and that's actually a crucial one for this talk. And another notation that I was actually using until I switched to this, which actually this is the notation that is more common in the Leavitt path algebra community. But the notation I was using was gamma, then slash J as a subscript.
Yeah.
Instead of dividing gamma by J. But this is just
I think it's better. Yeah.
But more complicated. It's better not to have subscripts. I sometimes deal with topics that require subscripts, superscripts, multiple subscripts, left subscripts, right subscripts, etc., etc. And I like to make it as easy as possible. Anyway, so these ideas, this correspondence between hereditary saturated subsets of vertices and graded ideals is again best viewed as a Galois connection and the corresponding Galois correspondence. And given a subset of vertices, we can consider the ideal generated by those vertices, which is automatically a graded ideal because vertices are homogeneous elements of grade 0, so they generate a graded ideal. And given an ideal, we can take the set of vertices that are contained in this ideal. And this, again, gives a Galois connection, except I'm cheating a little bit here. Here, the maps between the posets, if we take inclusion as our partial order in both on both sides, then it's not order reversing, it's actually order preserving. But we could take, for instance, reverse inclusion as the partial order on ideals, and everything would work out. In fact, in the theory of Galois connections, what I have been calling a Galois connection is sometimes called an antonym, antitone, an antitone Galois connection, and the Galois connections that preserve order are called monotone Galois connections and the corresponding Galois correspondences. Anyway, it's completely trivial. If they are order preserving, you just look at the upside down poset for one of them. Anyway, so the Galois correspondence resulting.
Go ahead.
Sorry?
Okay, so I have a question about this direction of this inclusion. Why not to take inclusion of complements then?
In fact, I do it the other way. I take the partial order on the quotients divided by.
Okay.
And yeah. So you could, of course, also take complements. So the point is, you have to reverse. You have to turn one of the posets upside down to make it fit.
Sorry, but you have to explain what you mean by the quotient, because if you have a subset, if you are contracting this subset, you do not obtain an empty set.
By a quotient, the quotient I'm taking is on the ideal side. So I'm taking
yes,
a quotient.
I know. I'm talking about on the side of vertices.
The vertices, I'm still subsets of vertices. I'm still ordering by inclusion.
Mm-hmm.
What I'm doing is I'm reversing the order on ideals by, instead of considering the ideals, I'm considering the quotients of the algebra by the ideals. And now, if there is an epimorphism from one quotient to the other, then the order is reversed. But it doesn't matter. And in fact, there is a reason. It's also reasonable to take complements, like you suggested. But this is all just an exercise. You can also define Galois connections and Galois correspondences with order-preserving maps by changing the properties a little, the obvious changes. So all this is really freshman mathematics. Anyway,
okay.
So we have this Galois connection between, which gives a one-to-one correspondence between ideals of the Leavitt path algebra, between graded ideals of the Leavitt path algebra and hereditary saturated subsets of vertices. So I have written it again. The one-to-one correspondence is given by associating an ideal to the vertices that it contains and associating a subset of vertices to the ideal that it defines. Now, in fact, the lattice of graded ideals of a Leavitt path algebra turns out to be Morita invariant. And the way to do it is via another one-to-one correspondence given by a Galois connection. And I'll say a little bit about that, but I should mention that for finite digraphs, which is what I'm talking about today, this was already shown by Ara Moreno Pardo in the first article on Leavitt path algebras. I don't remember exactly, but their idea is not too different to get the Morita equivalence, where we define the Galois connection. We sort of have to relate hereditary saturated subsets and graded ideals to the module category of the Leavitt path algebra. And I will say some more about that. The other thing I should mention is I'm saying lattice here, but of course a lattice is a special kind of partially ordered set where you have meets and joins, and the Galois correspondence actually preserves these meets and joins. Now, in order to get the Morita invariance, we need some Morita invariant properties and objects. So we have the monoid of what is usually called non-stable K-theory. So given, say, a unital ring, we look at the additive monoid of isomorphism classes of finitely generated projective R modules, the monoid operation being direct sum, coming from direct sum. And this is
May I have a question?
Yeah.
Speaking about Morita invariance and modules, are you talking about arbitrary modules or graded modules and graded Morita equivalence?
No, I'm talking about, for this, I'm not looking at the grading at all.
Okay, thank you.
This is regular Morita equivalence. Yeah. Now, it is interesting that the graded ideals can be gotten by completely ignoring the graded structure on the Leavitt path algebra via this process that I'm outlining now. But since the properties of being projective or finitely generated are categorical properties, non-stable K-theory, the monoid of non-stable K-theory, is a Morita invariant. And if you take the Grothendieck group completion of this non-stable K-theory monoid, then of course you get the K0 group, which is an invariant of the ring. Now, we say that a submonoid of non-stable K-theory is closed if when we have a sum, then both sum ends are actually also in the submonoid. Now, this is more classically. Sorry?
That should be A comma B, right?
That should be what?
A comma B belong to S, because you said both.
I said both, but who knows who's A and who's B? This is a commutative monoid.
Oh, that is true, yes. Yeah, but then you have no quantifier from B. It's kind of strange.
Yeah, it's automatic. I mean, A plus B is also equal to B plus A, and then you get that B is an S.
Yeah, you're right, yeah.
And I'm departing from classical terminology, and I apologize for that. I call it closed, but anybody who is doing monoids would call it an order ideal. Now, I am calling it closed because of the Galois connection that actually, again, streamlines these ideas, where in the Galois connection, when we look at twofold compositions, we get closure operators, and these are exactly the closed submonoids. So we have submonoids of non-stable K-theory, and we have ideals of the Leavitt path algebra, and we can define this orthogonality between them by considering all homomorphisms from the projective space to the quotient by the ideal. And basically, we say they are orthogonal if there are no non-zero homomorphisms. And of course, we have to do this for equivalence classes of projective modules, that's isomorphism types of projective modules, etc. But there is this Galois connection by taking the perp of submonoids or the perp of ideals, which results in a one-to-one correspondence with closed submonoids and graded ideals. And since closed submonoids are Morita invariant, graded ideals, the lattice of graded ideals is also Morita invariant. So we have an isomorphism between the two lattices. Now, in order to do what we want to do, of course, we want to understand what are ideals of Leavitt path algebras, all ideals of Leavitt path algebras. And they are well understood. I'm calling this the Cholak-Rangaswamy theorem. The history was Cholak showed that in the raw finite case, when the digraph is raw finite, which means there are no infinite emitters, ideals are generated by vertices and polynomials in cycles. Then this was generalized to arbitrary digraphs by Abrams, Bell, Cholak, and Rangaswamy. And then the generators were put, some redundant generators were eliminated, and it was sort of tidied up by Rangaswamy. So it started with Cholak and went through Abrams, Bell, Cholak, Rangaswamy, and then ended with Rangaswamy. So I'm calling it the Cholak-Rangaswamy theorem. And what it says in the case when the digraph is finite is we have canonical generators for every ideal. We have the vertices that are contained in the ideal, and we have polynomials in cycles where this cycle has no exit when we erase the vertices in the ideal, or all exits of the cycle are in the ideal. And such cycles contribute a polynomial generator if we think of the intersection of the algebra generated by that cycle and the original ideal J is non-zero. And the canonical polynomial generator is essentially the minimal polynomial of the cycle C in the corner algebra of the quotient. This is to make the generator unique. This is not the way Rangaswamy states it, but this is the version. It's equivalent, of course, and this is the version that's convenient for us. So that's the one I want to use. And to make these polynomial generators unique, we can take them to have constant term 1. But I should tell you how do we plug in a cycle, when we think of the cycle, of course, as an element of the Leavitt path algebra, into a polynomial. And the constant term 1 becomes the vertex, which is the source of that cycle, because that is the multiplicative unit in the corner ideal. So we are really working in the corner ideal.
Sorry, let me clarify one thing. When you say two-sided ideals, don't you mean graded? Isn't this theorem and this kind of classification referring just to graded two-sided ideals, not all of them?
No, I am now talking about all ideals. For the graded ideals are generated just by the vertices contained in that ideal. We do not need these polynomials. So the very nice result here says that all we need are the vertices in the ideal and some polynomial generators corresponding to certain exclusive cycles. So these are all ideals, but they are, of course, two-sided ideals. I'm not talking about one-sided ideals. In fact, we can talk about the space of all ideals. And in order, again, to put it in a more general framework, let me start by saying something about filtrations and the corresponding stratifications. So given any set, we can look at filtrations indexed by a partially ordered set. So I'm doing this a little bit more generally than usual. Usually we look at ascending filtrations and descending filtrations when the partially ordered set is like natural numbers. But here we are allowing indexing by an arbitrary partially ordered set. And a filtration is a order-preserving map from the partially ordered set to the power set of all subsets of the set. And of course, the subsets are ordered by inclusion. Given any such filtration, there is a corresponding stratification where the strata are disjoint. The filtration, of course, is not the elements of the filtration form chains, but the strata are disjoint. So we take a particular level of the filtration and throw away everything that came before, and those are the strata. And obviously, the filtration is given by the disjoint union of the strata chosen appropriately. Now, I'm not talking about a Whitney stratification or any such with more structure, because we have no structure on the set X that we are starting with. And we have a stratification of the ideals of the Leavitt path algebra indexed by the poset of graded ideals. And where an ideal belongs is indexed by the largest graded ideal that the ideal contains. And that's easily seen to be, you take the ideal J and you look at the vertices in that ideal, and you look at the ideal generated by the vertices in the ideal. So that's a subset of the original ideal. And that is the largest graded ideal that is contained in the given ideal. Now, we will actually need a finer stratification when the indexing set is ordered pairs, where we have the first being a graded ideal, and the second is a subset of the set of cycles, which of course have no exit in gamma/I, contributing polynomial generators to J. Each stratum corresponding to the ordered pair I beta is parametrized with a cardinality of beta tuple of finite non-zero sequences in the field F, or equivalently with polynomials where of positive degree with constant term 1. So these are the polynomial generators, and of course we can identify the polynomial with the coefficients. We don't use the constant term because that's always chosen to be 1. And we have a bijection. That's essentially what Cholak-Rangaswamy theorem is telling us. Between triples, where we have a graded ideal, which really corresponds to a hereditary saturated subset, a set beta of certain exclusive cycles in the digraph, and theta, which assigns to every cycle the canonical polynomial generator in that cycle. And the bijection is what I think you think what it is. And we have a perfect one-to-one correspondence between these triples and ideals of the Leavitt path algebra. So the ideal space is the ideals equipped with this stratification, and each stratum is given the parametrization by the coefficients of the polynomial generators. So now I want to talk about another digraph which we can associate to the ideal J. So this is a refinement of gamma slash J. And what we do is we start with gamma slash J, and we replace the cycles that contribute polynomial generators with loops. There is a way of doing that without changing the isomorphism type of the Leavitt path algebra, which I'm going to explain soon. And maybe this is best explained in an example, but first let me tell you how to do that. So whenever we have a cycle with no exit, you pick an arrow on that cycle and you disconnect it at its target. So you cut it at the target and then make it a loop. So we connect it so that its target now is its source. So what we have done is we have not changed the vertices. In some sense, the set of arrows is again the same, but we have changed how those arrows are attached. And the fact is the digraph and the digraph we start with and the digraph we get after performing this graph move give isomorphic Leavitt path algebras, and they are isomorphic as star algebras. And the isomorphism is easy to describe. So let me actually try to explain this graph move in an example. So we have the digraph gamma, which has this 3 cycle, which we are going to change into a loop. And of course, we have 3 choices for the arrow on that cycle that we can pick. If we pick the arrow E and cut it at its target, and then join it to its source, then we get the first digraph on the lower list. If instead we disconnect the arrow F and make it into a loop, then we get the second digraph. And if we do it with G, we get the third digraph. Now, all these 4 digraphs are distinct as digraphs. They are not isomorphic as digraphs, but their Leavitt path algebras are isomorphic. That's what the previous lemma stated.
Could you go back to the previous lemma for a second?
Sure.
If the digraphs are as above, which means what?
Which means that we take these cycles with no exit, some cycles with no exit, we take an arrow on that cycle and we cut it at its target and we make it into a loop. So that's the graph.
So it's a kind of move, right? But it's
Yes.
not related in any way to the moves that we know from, say, Efren, Soren, and Soren. It's not any outspeed shift or in-speed plus, nothing of that sort.
It's not exactly that, but in fact, there are variations on this. And in fact, we've used another graph move similar to this, and they can be obtained from each other using shifts and outsplits and things like that. So let me tell you that, and in fact, the basic thing that's happening is there is a Morita equivalence given by something that I did a long time ago called reduction.
Yes.
And here
I know reduction.
we do a version of this by adding some sources, and reduction gives a Morita equivalence, but these moves give an isomorphism.
So isn't it called reduction plus?
What Søren calls reduction plus wouldn't do exactly this. He would, instead of having this tail that we get, so let's look at the maybe the second example in the middle. So you see the cycle was replaced by this tail. Maybe actually that's not a good one. Let's look at the first one.
Okay.
So instead of that tail, Søren would have one vertex and several arrows emanating from that vertex, going to the target target of the tail.
Yeah.
I'm saying Søren because I know him and I don't know Ruiz, but it is, of course, their joint work.
Yeah.
And my third graph move would instead, again, not have tails, not these paths, but instead would have multiple sources, one for each arrow in the tail, and only one arrow emanating from each source going to the target. And all these are isomorphic. So all these graph moves give you isomorphic Leavitt path algebras.
Now, correct me if I'm wrong, but I believe that they have a theorem saying that if your graph is finite, which is what you are doing here, then I don't remember the exact premise, but somehow that everything can be obtained by a sequence of the moves they describe. And
yes,
of course not.
Yeah, I mean, you have to say, so this sort of gives a canonical form for the digraphs, which have the same Leavitt path algebras, etc. But I'm not going in that direction at all. All I want to do is it's convenient for me to replace these cycles that contribute polynomial generators with loops, because I can describe what's going to happen to the loops very easily. So
I'm fine with this. My point is that I would like to understand whether your moves can be sort of by force, by general theorem, always obtainable from moves that Søren describes.
Yes, they can be. Like I said, there are three procedures. This is one of them. Another is what Søren calls R+. And there is a third one, which is in another preprint of ours about classification of Leavitt path algebras. And they can all be gotten from each other fairly easily. And you can show that they are, and using definitely outsplit, and maybe only outsplit, but anyway.
Okay, thank you.
This is the one that I want to use today. And now we can describe another digraph coming from the pair of a digraph and an ideal of the Leavitt path algebra. So gamma double slash j is obtained in two steps. First, we replace gamma slash j. So we erase all the vertices that are in j, and we get gamma slash j. Then the cycles that contribute polynomial generators to the ideal, we replace those with loops as described before. And then what we do is we delete each loop, replace it with a bunch of sinks. And the number of sinks is the degree of the polynomial. And then each arrow ending at the base of that loop, we replace again with arrows, each ending at a distinct sink, replacing the loop. Again, this is best explained with an example. So let's say that we have this digraph, gamma, which is a 4-cycle and an arrow from that 4-cycle to a sink. Now, we have an ideal generated by the polynomial of degree 3 that I have given before, which basically is 1 minus alpha x times 1 minus beta x times 1 minus gamma x, where alpha, beta, and gamma are non-zero elements of our coefficient field. Now, it turns out that whenever you have a polynomial generator, then every vertex that you can go to from that cycle is also in the ideal. So by giving this as a generator for the ideal, we automatically get the sink W, because we can go to W from the cycle with a path. W is automatically in the ideal generated by this polynomial. And in fact, W is the only vertex that is contained in the ideal generated by this polynomial of degree 3. So the first thing we do, gamma slash j, is to erase this vertex, the W, and of course the arrow that goes to W. And now we have a single cycle. And then we do the graph move that was described before, where we replace one of the arrows on the cycle with a loop. And then we sort of, instead of this loop, we put in 3 vertices. And the 3, we have 3 because 3 is the degree of the polynomial. And for every arrow that ended at the base of this loop, we put in an arrow going, starting where it did start, but now ending at one of these 3 sinks. So gamma double slash j is the digraph that we get at the end of this process.
Sorry, now I'm completely confused. What is lambda?
Lambda
What's
is
the relationship
digraph
between lambda and gamma? I mean, do you mean that lambda double slash j or what?
No. Lambda is the intermediate digraph we get when we make the cycles into loops. The cycles that contribute polynomial generators into loops.
So lambda is obtained from gamma by one of these moves, right?
Exactly, yeah.
Okay.
Yeah. And then from lambda, so it's really, it's easier for me to describe it in 2 steps. But finally, we start with gamma and we end with gamma double slash j. And what happens is that the cycle is gone and it's replaced with a bunch of sinks. and the number of sinks is the degree of the polynomial. And we do this for every polynomial generator of the ideal. May I continue? Now we say that an ideal is DLF if each polynomial generator is a product of distinct linear factors. And this should be true for every canonical polynomial generator of the ideal. Now, if an ideal is graded, then it has no polynomial generators. Then it's vacuously DLF. And this definition is in terms of the digraph, but actually it's an algebraic property. And that's one of the main theorems, which says that we take an ideal of a Leavitt path algebra and we look at the quotient. The question is, do we get a Leavitt path algebra, or do we get something that's not a Leavitt path algebra? And we get a Leavitt path algebra if and only if the ideal is DLF. That is, all canonical polynomial generators of the ideal were DLF, that is, were products of distinct linear factors. In other words, these polynomials had all their roots in the field and there was no multiplicity. Each root came with multiplicity 1. Now, in one direction, we have to show that if the quotient is a Leavitt path algebra, then the ideal is a DLF, and that requires some work, which I don't think I have time to talk about today. The other direction should give you, if we have a constructed proof, if it is isomorphic to a Leavitt path algebra, what is the digraph whose Leavitt path algebra is isomorphic to the quotient? And of course, that's why we went through all this trouble with gamma double slash j. The quotient of the Leavitt path algebra is isomorphic to the Leavitt path algebra of gamma double slash j. So that's the Leavitt path algebra. That's the digraph which gives you the Leavitt path algebra. Now, if the coefficient field is large enough, then it turns out that the obstruction to the quotient being isomorphic to a Leavitt path algebra is the nil radical or the Jacobson radical of the quotient. It turns out that the nil radical and the Jacobson radical of the quotient in general are equal to each other. So we can just say radical. And the theorem is, when the field is algebraically closed, then the nil radical of the quotient equals the Jacobson radical of the quotient. And when we divide the quotient by its radical, then we get always a Leavitt path algebra. So that's basically a slight strengthening of the theorem I started with that says that the quotient is a Leavitt path algebra if and only if the ideal is a radical ideal. I should say something here that in the commutative case, the nil radical is exactly the set of nilpotent elements. So you look at nilpotent elements in the ring, and you can easily show that they are closed under addition and multiplication. Now, that's not the way you define the nil radical in the non-commutative case. In general, in non-commutative algebra, you don't use elements, but you use ideals. Like, for instance, in the definition of a prime ideal of a non-commutative ring. And here, in non-commutative setup, in non-commutative ring theory, the nil radical is the largest ideal which consists only of nilpotent elements. That doesn't mean that, so if we have trivial nil radical, that doesn't mean that you have no nilpotent elements. If you, the nil radical of any Leavitt path algebra is trivial. But a Leavitt path algebra has zillions of nilpotent elements. Yeah. Almost any PQ star you pick is going to be nilpotent. But there is no ideal that consists exclusively of nilpotent elements. So that's the nil radical story here. Now, it also follows from the sufficiency of the criterion that the quotient is a Leavitt path algebra if and only if the polynomial generators are DLF, that a generic quotient of a Leavitt path algebra is isomorphic to a Leavitt path algebra. Now,
sorry, what do you mean by generic? I'm confused. What do you mean by generic?
Yes, yeah, I'm about to explain.
Okay.
So remember, we had the stratification and the parametrization of the space of ideals. So what I mean is that something is an open and dense subset in some topology. Now, what are we talking about? Each stratum, which corresponds to a pair, a graded ideal, and a collection, the collection of cycles that contribute polynomial generators. Now, remember, we could parameterize these with polynomials because each such cycle was assigned a polynomial, and then we got a unique ideal that corresponded to this assignment, and it's a one-to-one correspondence. Now, the polynomials, of course, have arbitrary degree. The constant term is 1, but the rest of the coefficients are arbitrary, except we are not allowed to pick the polynomial 1, so we cannot pick every other coefficient equal to 0. And then we can further filter these by the degree of the polynomial. And when we do that, we have a one-to-one correspondence between the affine space Fn with 0, the origin deleted, and polynomials of degree less than or equal to n plus 1, n less than or equal to n. And that, of course, we can give topology to that set. For an arbitrary field, the topology we give would be the Zariski topology. But if we were working over complex numbers, we could also give it the Euclidean topology. Now then, of course, polynomials have arbitrary degree, so this is an infinite space. So we can take the limit of these topologies, or the topology generated by these topologies for each degree. And this is true for each cycle. And we have a set of cycles, so we give the product topology when we do this over a bunch of cycles. So the stratum, which corresponds to a graded ideal and a subset of cycles, gets this topology that I have just described. And when the field is algebraically closed, then the set of DLF ideals in each stratum is an open and dense subset with respect to this topology. So that's what I mean by generic. Have I answered your question?
Yeah, thank you. Yes. Mm-hmm.
Okay, now the rest, for the rest of the talk, I just want to talk about a few examples, and most of them are easy examples, and I think I've only got a few minutes anyway. So for instance, we could start with another digraph that I like very much, which corresponds to a two-dimensional quantum sphere. And a very easy example is we can take the ideal generated by one of the sinks, say W, and here we don't have any polynomial generators. The ideal is a graded ideal. So what we get when we divide by that ideal is the Leavitt path algebra of gamma slash j. So that's a single slash. And that, of course, corresponds to erasing the vertex W. And then we get the digraph that corresponds to a quantum 2-disk, the Toeplitz digraph. And we have this epimorphism going from the Leavitt path algebra to the Leavitt path algebra mod the ideal. And the commutative version of this would be we have continuous complex valued functions on the 2-sphere, and we restrict them to the upper hemisphere. That corresponds to the quotient map. Now, another easy example, we start with a single loop, and we already know the Leavitt path algebra is the Laurent polynomial algebra. Now we divide it by a polynomial generator, which is V minus the square of the loop. And this time we get the Leavitt path algebra of gamma double slash j, which just replaces this cycle, this loop, with 2 isolated vertices. But this is true because the polynomial was 1 minus x squared if the characteristic of the field is not 2. If the characteristic of the field is 2, then 1 minus x squared is, of course, 1 minus x quantity squared, so the roots are not distinct, and we do not get the quotient to be isomorphic to a Leavitt path algebra. We can do something similar, instead picking 1 plus x squared instead of 1 minus x squared as our polynomial. And then it makes a difference whether the coefficients are, for instance, real numbers versus complex numbers. If the coefficients are complex numbers, then the roots are distinct and they are in the coefficient field. So we do get the quotient being a Leavitt path algebra, in this case of 2 isolated vertices. But if it's real, then the roots are not in the coefficient field, so we do not get a Leavitt path algebra. The quotient is not isomorphic to a Leavitt path algebra. And of course, we can jazz up this example to a number of roots instead of one root. So here's another example where we start with the digraph corresponding to a 5-dimensional quantum sphere. And we can take the ideal generated by one of the vertices, W, and a polynomial 1 minus x squared in the cycle C. And first, we may divide just by the graded ideal generated by the vertex W, and then we get the digraph corresponding to a quantum 3-sphere. And then we further divide by the ideal, so the polynomial, and then the 3-sphere becomes a 2-sphere, if you'll excuse my quantum language, in the quotient. If the characteristic is equal to 2, again, we do not get a Leavitt path algebra because the roots are not distinct. We have a similar example where we have a polynomial of degree 1. So the cycle is replaced with a single sink, and this is this corresponds to an inclusion of a 2-disk into a 3-sphere, which you can factor through a 2-sphere. And the final example, I'm hurrying up a little because I have 1 minute left. And in the final example we can take the polynomial 1 minus x to the n. And if the field contains the nth roots of unity and they are distinct, so that n is not dividing the characteristic of the characteristic of the field doesn't divide n, then we get because we have a polynomial generator involving the loop E, everything we can go from the loop E by a path is also automatically in the ideal, so we lose W, and then when we divide by the polynomial generator, this time we get gamma double slash J, where we have n sinks that correspond to the loop when we do our process. So I've listed a few references. A standard reference, of course, is the only book on Leavitt path algebras by Gene Abrams, Pereira, and Mercedes Les Molina. I'm mentioning 2 of the papers by Cholak and Rangaswamy on the ideals for quantum spheres and projective spaces as graph algebras. There is, of course, Hong and Szymanski. Our preprint, which includes everything I've said and more, is on the archive. Leavitt started this whole story with the module type of homomorphic images. This is the last paper of Leavitt in that direction, which is from 1965. And all I've got left is to thank you for your patience.
Thank you very much. I have many questions, so let me first ask everybody else. Dimitri?
Going first.
No, but we are clapping. It's not a question.
I need to think. I think I have.
Okay, so if you think about the question now, Adam.
I'm happy. I'm
Ludwig.
happy. Very nice talk. Thank you.
Thank you.
Okay. Okay, so it seems like it's just the 2 of us. So let me start. Can you go back to this previous slide? No. I want to see a graph of the Hong-Szymanski ball. No. We have like S5. Okay. We have like no, S5. On S5 graph.
Oh, you want
S5?
S5?
Yeah. Okay. Now let me see. I should be able to write. Okay. I know that these things are isomorphic, but can you remind me how you get this isomorphism? Because traditionally you would have one more arrow going here. I know that there's an isomorphism which is not equivariant. So can you remind me how you prove that it's the same algebra even when you delete this arrow?
The isomorphism, as you said, is not graded, but it is a star algebra isomorphism. Now, of course, you use a move called shift. So let me try to remind you the move.
No shift.
If you know shift, that's what you do. There is only one arrow with source from W. And that arrow corresponds to the red arrow that you put there. But from U, we have an arrow that has the same target as the arrow from W, but we have 2 more arrows. And in shift, what you do is, sorry, I didn't say this correctly. I should have done it with V. Okay, I'm going to say it again. On V, there are 2 arrows.
Okay, when you do a shift, you have 2 vertices. So which are your 2 vertices for the shift?
U and V.
U and V, fine.
Yeah, and when you do U and V, what happens is you delete the arrows from U to V and the red arrow that you drew from U to W, and then you replace it with an arrow from U to V. So now you deleted two arrows, you put one arrow back, but the arrow you put back looks like one of the arrows you deleted. So the digraph becomes this.
So with the shift loop, okay. Yeah, the shift loop, of course, is not equivariant. Okay.
The shift, yeah, it's not equivariant under the gauge action, which is what a C-star algebraist like yourself would say. I would say a shift is not a graded isomorphism, but it is a star algebra isomorphism. Yes.
Okay. Now, can you go back to your main theorem?
Which main theorem? Can you erase your arrow?
Yeah, I'll try to erase my arrow. Let me see. Okay. Yeah, I think that's your main theorem, right?
Well, the characterization of ideals with quotient.
Yeah, your Nullstellensatz theorem, right?
Oh, Nullstellensatz. That's the Nullstellensatz, yes.
So, would it work for graph sister algebras?
I haven't thought about it. I mean, see, I am not an expert on graph C-star algebras. You are.
Well, that's why I'm asking the question.
Yeah,
I'm pretty sure that one way it should work because graph sister algebras are just the universal enveloping sister algebras of Leavitt path algebras.
That's right.
And you have this inclusion, yeah. But so one way it surely should work. But if you have isomorphic graph sister algebras, it by no means for a given graph, by no means it implies that you have isomorphism of Leavitt path algebras because these are just dense subsets. So.
Yeah, of course, it's too large. But
this problem with Kunz splice, right? This isomorphism you have for Kunz splice on the level of graph sister algebra is an open question. Can you do it for Leavitt?
Exactly. Yeah, so I really don't know the answer, and I admit that I haven't thought about it at all. But it is, of course, a very good question.
Yeah. Okay.
With either way, I mean, if the answer is yes, it's very nice. If the answer is no, that's also interesting.
Yeah, but this is just whichever way it goes, it's interesting. Now, let me instead of a question, let me make a brief comment. So, yeah, that's true. When you take Leavitt, then this Jacobson Leavitt algebra, that is Jacobson radical, always vanishes. But I remember playing around with path algebras. And then you can very easily determine what is the Jacobson radical of any path algebra. And then you can somehow, what you can do, if you divide this path algebra, I mind you, path algebra, not Leavitt path algebra. If you divide path algebra by its Jacobson radical, then you can write it down as, at least under some assumptions, I don't remember, it's been ages ago when I did it, then you get another path algebra, but with a graph which is appropriately modified. You turn certain paths into edges and stuff like this. It's just a comment, but it's very much in your spirit, right? Except that I played with path algebras instead of Leavitt path algebras.
It is actually interesting, and I am interested in it. Do you have it written up anywhere that we can look?
Yeah, I should have it somewhere in my lecture notes. I can send it to you. Yes.
Thank you. Thank you. Yeah.
It
is in that spirit. Yeah.
Yeah, this is in the spirit. You see, during the pandemic, I was teaching 3 courses, 3 semesters on graphs and graph algebras, and somehow, when I was teaching, I would try to understand everything which goes in between. So I asked myself this obvious question. I was really surprised that in this famous blue book about path algebras, the Bible of path algebras, they just state this theorem about Jacobson radical only for cyclic graphs. But you can just as easily find it for any graph whatsoever, no assumptions. You can just write a formula for this Jacobson radical, which is absolutely crystal clear. And I couldn't understand why it was not proven in this book, so I just proved it for my lecture course. And then if you play a bit further and take this quotient, you can say, aha, so at least under some assumptions, you can say that this is a path algebra of another graph. As I said, when some of paths are now shrink to edges. But okay, this requires a separate debate. What else I was thinking about? I looked up. So I concur with you. I stand corrected. You're right. Hawaiian earring is always referred to when you have infinitely many loops. You're right. So I stand corrected. I somehow, it was my mistake. So thank you very much. But okay, we have Kunt algebra O infinity. So we like Hawaiian earrings anyway.
But to me, I mean, I'm a topologist, to me, Hawaiian earring comes with the topology.
Yeah, you're right. This is how it's written in Wikipedia. And I was also thinking about the notation because, honestly, for me, having this slash, which is commonly referred to as a quotient, it's disturbing. So. I tried to look at my paper what notation we use, but we did it the other way around. We would always take a subgraph in a graph, and then we would describe J instead of describing the graph. You do it the other way around. But I would be more happy with having like a set minus, like gamma minus J at least. Because you are subtracting some vertices, so you can say, okay, it's not really an ideal, you mean vertices that are inside the ideal.
I am okay. So let me try to make an argument for this. So the spirit of non-commutative geometry is we have the algebra of functions, and that's what determines the space. There is no space, but we have the algebra of functions. So in the algebra of functions, what we are doing is we are dividing by an ideal. So the space and what I actually also used at some point, but not in print so far, at least I don't remember, the notation gamma set minus J, which I wasn't happy about because we are not subtracting an ideal. We are subtracting a bunch of vertices. Yeah, anyway, so there is always a problem with notation. Yeah.
I mean, but you see, there is something, slightly deeper in my being disturbed by this, because by using this, in my opinion, completely unacceptable notation that is used in this Leavitt book and so on, calling it at least you didn't call it a quotient graph. So I'm extremely grateful that you didn't call it a quotient graph.
No.
For me,
it's gamma slash J.
It's obscene. Yeah, it's obscene. You just use a slash, but at least you didn't call it a quotient graph, which for me is abomination. And because you see, it also totally ignores the contravariant nature of a Gelfand-Naimark functor, or going to algebras is contravariant. So quotients go to subs, and subs go to quotients.
Exactly. Yeah.
And if you reverse it, you are just losing sense of any geometry or topology. Yeah. Okay. So I think I'm okay. Maybe one more thing. Can we go back and can you explain to me this move again? Because as you know, we are working on moves right now with Elizabeth. So I'm really very much interested. Okay, so how do you do these moves?
Which one? Replacing the cycle with a loop? Or,
yeah, exactly.
Yeah.
Yeah,
yes.
Exactly, like here.
Yeah.
Okay, so I start with gamma. That's where I start, right? This is my graph which I start. I spot a cycle here.
Yes.
Yeah, that's gamma. Yeah, I spot a cycle here. So what's the definition of my move?
Well, the move is not well defined because it depends on a cycle and an arrow on that cycle you choose.
Okay.
So it corresponds to a cycle and an arrow. It's an order.
Okay, fine. So I have a pair, a cycle and an arrow. Okay.
That's right. Yeah. And then you take the arrow, you disconnect it at its target.
Okay.
And you connect it to its source.
Mm-hmm.
You take
that's
the
it.
arrow, yes, you get it. Yeah, that's what you do when you do E. That's exactly what you get.
And you are saying that I can obtain it by these other moves like what? Alt split and what?
Maybe shift. I don't remember now. I have to think. So if you did, it's easier for me to think not with Eilers and Ruiz R plus, but with another move that's in another preprint, which I call the pincushion. So you can take the cycle and you can make it shorter by reduction. So you make you eliminate vertices on the cycle. So, for instance, you could eliminate the vertex at the bottom. And what you do is you replace all paths of length 2 passing through that vertex with an arrow. So
yes,
paths of
exactly.
length 2
That's
become,
reduction, yes.
Yeah, that's reduction. Now, there is this reduction with bells and whistles where you also take this vertex that you eliminated, and you make it a source. You make it a source, and you connect that vertex to the target of. So I should say it like this.
Exactly. Let me jump in because it's very, very important. You see, this is in fact under some assumptions, but very mild assumptions. This is the inverse of a shift move. So reduction task, as you just described, is just under some assumptions. It's exactly the inverse of a shift move, but both of them describe one and the same admissible graph homomorphism.
That's correct. Yeah, one of them is the inverse isomorphism.
Yeah.
And now you can repeat this with other vertices on the cycle that you replace. Now, if you do it my way, or Søren Ruiz way, you get only one extra vertex. In R plus, in Søren's R plus, you get only one extra vertex with several arrows going into the base of the cycle. In the pincushion, you get as many arrows as you eliminated, with only one arrow going from each source again to the base of the cycle. Now here, instead of that, you get a tail. But if you have a tail, so if you have a path, then you can eliminate vertices on that path again with such moves, with the same move, which will slowly make that path shorter and shorter. And at the end, you are going to end with the R plus move or my pincushion model.
What do you call your move? Pin push? Pin push?
Pincushion. So I'm sticking pins. I'm sticking pins. So in reduction, you replace every path of length 2 passing through the vertex you are eliminating with arrows. And then the vertex you are eliminating, I make into a bunch of sources. How many, the number of arrows that emanated from that vertex that you eliminated. And so those are pins that I'm sticking into the pincushion.
Okay.
But it's easy to see that these are all equivalent.
I hope Elizabeth is familiar with all of this, right?
I hope so also.
Okay.
I did describe it to her. This is, this is written up in another paper in the archive, which is called, I think, Classification of Leavitt Path Algebras of Gelfand-Kirillov Dimension Less Than 4 or something like that.
Okay, jolly good. Dimitri.
So one quick question because I have to go. Not question, mostly a comment. You might be interested. Well, first of all, thanks for the very nice talk. Second, you might be interested to look into sub-product systems, where again you have a Nullstellensatz, where you have an algebra, well, the ring of non-commuting variables and non-commuting variables, and over the complex numbers, let's say, and you care about ideals, and you can lift all this structure, the quotients, into Hilbert spaces, and then you construct Toeplitz algebras, Kunz-Pimsner algebras. It's a generalization of the actual Toeplitz and Kunz-Pimsner algebras on Fock spaces, where instead you do not look where these correspond to full product systems, and by quotienting out by ideals, you could say that you work in well, that's not formally correct, but you would say you work in sub-Fock spaces. And then you end up getting a lot more algebraic structure. And you do have a Nullstellensatz, a non-commutative one. That's work from Salit and Solel from the 2010.
Would you be kind enough to send me a reference, because I'm not familiar with this at all?
Of course.
Yeah, thank you.
Of course.
Okay.
Right, and you do have graphs, like all Kunz-Krieger algebras. You can update them through that. You quotienting out by monomials, basically.
So that's clear.
Yes, exactly.
Okay.
Like by forbidden words.
Yeah, forbidden words.
Yes.
Okay.
Thanks.
Okay, so let's thank our speaker again and wind it up. Thank you. I stop recording.
Thank you.
Thank you. Thank you for listening. I have office hours and